Hi, I'm Liam. Today I'll present our midterm report for CS506 on food insecurity and chronic disease. The goal of this project is to examine how food access relates to food insecurity and, in turn, how food insecurity is associated with adverse health outcomes. At a high level, our study follows this straightforward pathway. To explore these relationships, we collected data from the USDA's Food Access Research Atlas, Feeding America's Map the Meal Gap dataset, and the CDC's Places dataset. Rather than merging all the data, we split the pathway into two relationships across 2 years. The first link looks at how low food access relates to food insecurity using data from 2015 when both the USDA and Feeding America datasets align in time. The second link explores how food insecurity relates to chronic health outcomes, using Feeding America's 2017 data combined with CDC's Places data, which is based on 2017 and 2018 surveys. This setup allows us to examine each step in the causal chain independently while still getting a broader picture of how structural inequalities in food access may contribute to health disparities. Before splitting the data, we performed exploratory analysis on all three datasets. We identified key metrics for each, for example, food desert population, food insecurity rate, and average chronic disease prevalence, and plotted them as county-level heat maps across the U.S. What we found was a consistent regional pattern. Counties in the Deep South and Southeast showed low levels of food access, high food insecurity, and high rates of chronic illness. This overlap suggests a potential strong association between these variables, supporting our decision to model these relationships further. To prepare the data for analysis, we created two clean datasets, one for each causal relationship. Since these sources come at different geographic levels, we needed to standardize them. The USDA Atlas data is available at the census tract level, while the other datasets are reported by county. To align them, we derived FIPS codes from the tract identifiers and aggregated all tract level data up to the county level, using either sums or population-weighted means, depending on the variable. This process allowed us to merge everything on a consistent county basis, giving us two ready-to-model datasets, link 1.cvs for food access and insecurity, and link 2.cvs for food insecurity and health outcomes. To quantify these relationships, we applied predictive models for both links. To prepare the data for the models, we trained on 80% of the data and applied PCA to reduce dimensionality. Interestingly, low income, poverty rate, and SNAP status were structural features identified in PCA as consistently correlating with high food insecurity. In both cases, random forests were the strongest performers with the highest R2 scores and explained the most variance. They were able to capture nonlinear relationships that linear regression could not. Next, we used clustering to search for patterns in the data. We tested three algorithms, k-means, db-scan, and agglomerative clustering using complete link distance. A visualization of this clustering is on the side. To evaluate the clusters individually, we looked at the silhouette scores, which tell us how cohesive and well separated our clusters are. All of them fell within a range of 0.79 to 0.83, implying they were. To compare them to each other, we used the Adjusted Rand Index, or ARI. All methods place the majority of counties in a single cluster, implying that across all features, the counties are fairly consistent. Further analysis is needed to identify which counties tend to fall into the smaller clusters and why. Our next steps include refining our models with hyperparameter tuning to improve performance, conducting subgroup analyses, exploring feature importance for interpretability, and different dimensionality reduction techniques, including TSNE or feature selection. Thank you for your attention.